Hello and welcome to the Microsoft AI Show. I'm Sonia Koptiev and I'm here today with Niall. Hi, Niall.
Sorry, hello.
So tell us a little bit about yourself and what you've been doing.
Sure. So I'm a bioengineering PhD student at the University of Washington, and I'm actually doing an internship now with the Cloud AI Prototyping and Innovation team. So my research is mainly on improving brain-computer interfaces.
Okay, wow.
By understanding more about how our brains understand mistakes.
Okay.
And my research project here is less about improving brain-computer interfaces directly, but more about exploring opportunities for AI in neuroscience and how we can use different Azure tools and services to, kind of benefit this.
Very cool. I think this is the first time ever we're, touching into anything neuroscience related. So this is fantastic work. So tell us a little bit of how you've been using Azure Machine Learning Workbench and Jupyter Notebooks and what you found.
All right. So with Azure Machine Learning Workbench, I've just put together some very basic notebooks inside the program. And inside here, I have a few different examples of some code that you can run. But let me first step through just a basic introduction so that we can just first get a look into what EEG data might look like.
Okay.
And EEG here is one form of recording brain data. So there's a lot of different ways that you record information from the brain. And one popular way is through recording electrical activity from the scalp.
Okay.
So this doesn't require any surgery. It's just you pretty much grab something that looks like a swim cap, and I can actually scroll down here. It kind of looks like that,
Okay.
and has a lot of electrodes on it. This is just one example, but there's a lot of different products that can record this electrical activity. And from there, you can get information from a lot of different places. And so we know that our brain has a lot of different sections responsible for different things. And there's a lot of communication between different parts as well. With EEG, we can get a general understanding of when there's more activity in certain areas than others.
Okay.
But because it is non-invasive, it's very broad. So we don't have the spatial resolution as if we had an invasive method or fMRI, for example. But go ahead and feel free to ask questions.
Jennifer Marsman actually does a demo of this that's also AI focused, right? And she uses the brainwave kind of
emotive epic.
Yes, exactly. So can you talk just a little bit about the amount of data generated with something like this swim cap approach? And because obviously it looks like it has a ton more nodes than what the other one does. So from a order of magnitude type of perspective of how much data we would actually be dealing with.
That's a good question. So with the emotive epic, which is what Jennifer was using, that is, there's two different products. There's a smaller one that I believe only has 2 or 4 electrodes.
I think it's 7 or 14.
And then the higher one, 7 or 14.
Yeah.
So I believe she was using the higher one, right?
Yes.
Okay. So with that one, there's about 14 different electrodes that are recording electrical activity over time.
Okay.
And so when we're recording things over time, we're taking a lot of samples, typically around, for EEG, let's say maybe 1,000 hertz is like the higher end.
Okay.
That's what I'm used to for invasive, at least. So with this, instead of having 14, you have around 64.
Oh, wow. Okay.
So that does really increase it.
Yeah.
And depending on what you're recording, you could record for just a couple minutes, or you could go for a lot longer.
Sure.
So for example, sleep EEG, they're recording the entire night. So it's a lot of data.
Right.
All right. So if we just go through here, this is just a very basic introduction to EEG notebook that I wrote, but let's go ahead and just run some code instead of explaining exactly what EEG is. So these first 2 cells here are for working specifically with Azure ML and making sure that we can log history within Workbench. But because this is just more of a demonstrative notebook, I won't be necessarily focusing on that. I'll just be showing just basic running some cells. So this is in Python. I'm just going to do the basic importing of libraries, making sure everything works just fine. Should take just a few seconds. There we go. Okay. And so now that that's imported, let's go ahead and define where the data is located. It's just in a folder inside the project.
Okay.
Okay. And then here's where we're going to start using some of the M&E functions. So here, EEG data can be stored in a lot of different formats. Popular ones are the EDF format, which is a standard European data format for brain data.
Okay.
.mat is another favorite of a lot of people since it works with
MATLAB.
Which is very popular. But this is in the .fif or FIF format, which is specific to M&E, but includes a lot of information and is very convenient. So let's go ahead and load that in. And it's loading. Okay, there we go. And so now we can see what raw contains. So inside here we can see that there's a list of bad electrodes, so things that we don't want to use in our analyses, which is very convenient. channel names, just different descriptors and all these things. So instead of looking at this text list, let's just go ahead and explore some of the information. So go and load this. It's just basic channel names, lots of MEG channels. Okay, and this is where we can actually start to dig into stuff.
Yeah.
All right. So because there are a lot of channels, this is kind of cut off. I only loaded a few just to have examples so it doesn't take forever to load.
Okay.
So here you can see this is what basic EEG signals look like. They're essentially just like a lot of squiggles over time.
Yeah.
And that's what they are. But from this, just looking by eye, unless you're a very trained professional, it's hard to determine, what's going on inside here. So inside this, you can scroll around and look at different time points. And it's a little slow here. There you go. And you can see these huge spikes here and there.
Sure.
Which, we don't necessarily want to consider in our analyses, or maybe we do. Depends on what we're looking for.
Okay.
But this is just the basic view of EEG. Let's go ahead and stop this figure since it is interactive. Let's go ahead and power off there. Okay. There you go. And now we have a snapshot of the figure.
Okay.
So it's nice that in the notebook you can actually explore the data. And depending on how you have matplotlib set, you can have it pop out in a window or just have it contained inside here. And so I have a little explanation about filtering in here. And then you can also filter the data and view the that's okay. And view the EEG data after it's filtered as well. I won't run this cell because it's the same as before, but this is just a snapshot of how it looks like afterwards. And you can see that's a lot cleaner.
Yeah. So you've cleaned up the noise.
Yes.
Or the library's allowed you to clean up some of the noise around all of the electrical surges. Okay.
Because in the US, at least, it's around 60 hertz, where a lot of the just like common source noise is. So we typically try to band pass or low pass. So we don't include that 60 hertz noise or any harmonics.
Okay.
So this here is just a basic, I believe, 1 to 40 hertz bandpass filter. Yes.
Yep.
Yep. So that helps get rid of the general noisiness and also some of these underlying slow waves as well.
Yeah.
Okay.
Oh, this is great. So basically, you've been able to not only import all of this massive sets of data, but also within the notebook, just process through it and be able to analyze it and remove the noise and clean it up a bit. And that's great.
Yes, and so one thing I do want to say is that because it is such a weird file format, it's not like a regular CSV or anything you can work with.
Yeah.
You can, if you want to convert things, export to CSV, which I have in another notebook. But since this is a nice contained single file, but you don't want to, wrangle with everything in a common data format, it's nice that we can work with it in the notebooks here.
Yep.
And we don't have to necessarily rely on the very nice data importer feature here, which is great. But if that doesn't work with what you have, notebooks are totally fine. And same with regular custom, just Python or R code.
Yeah.
So that's just an example. But one cool thing is that, let me just show you this thing here, is that you can also visualize things like the electrode positions. And if I had this as an interactive, you could click around and see what the electrode names are. And this one as well, right now, just to keep the notebook fast, I don't have it interactive. But you can enable the interactive one by uncommenting this line. And you can drag this around and actually see the 3D shape of where the electrodes are on the head, which is very convenient.
And so how would you do this without Workbench or without the notebooks being integrated? Like how would you be able to process through and visualize the data before that?
Sure, so good question. So with this kind of, this notebook here, it's mainly just Python code, but nicely formatted so that we have explanations along the way. But if you weren't to use a notebook format and just run just a Python script by itself, you can still get these plots out, but it'll seem like a lot of disparate plots just coming up one after the other, and there's no nice explanation such as this in between. So I think this is just a really nice way to organize your thoughts and get everything working nicely. Of course, you could use something like Spider to keep things organized, but it's nice to have everything in a notebook format, in my opinion.
Absolutely, and one nice page.
Oh, thank you.
Yeah,
and so this is just like an example of these kind of things. So it's pretty much a continuation of how you can look through EEG data, and I'm just explaining basic things about Fourier transform here, and how you can plot different types of plots as well. So instead of just looking at where the electrodes are placed and the raw EEG signals, you can also look at things like, after you run basic analyses, looking at the power spectral density, for example,
So what would that tell you?
So this would tell you.
For all of us non-neuroscientists.
Totally fine. So this is just a common technique to understand more about how much essentially power is within a certain frequency band.
Okay.
So our brain signals, when we record the electrical signals, you can think of it as a combination of a lot of different oscillations.
Okay.
So you can think of it as, actually I'll scroll up to one of my explanations here. Let's say that we have an example brainwave that ultimately looks like this.
Yep.
But it might actually be a combination of these 3 waves here.
Okay.
This is very simplified, and of course, like not exactly this simple, but this is the basic principle on how our brain waves are kind of formed.
Okay.
Since there's a lot of activity in the brain, and whenever you have action potentials between different neurons, for example, they generate some electrical activity that we're recording. So when there's a lot of activity between different populations and they're going at different rates, you can think of them as oscillations in a sense.
Okay.
So that's what we end up getting, things kind of like this.
Okay.
So this plot over here is just a standard way of visualizing how much amplitude or power we have within each of those different rates of oscillation. And so a standard thing is that you'll see, here this is just all the different channels together. You'll see that decreases as you get higher in frequency, just a basic physics rule. But this is useful, for example, if you're looking at, in a brain-computer interface, for example, you might want to determine whether someone is trying to intend to move something or not. So when that happens, there's a certain increase or decrease in, for example, the beta band.
Okay.
And so you can look at the value within that band. So let's say about here, like 13 to 30 or so. And so if you look at the height in that area in one condition versus the other, you can kind of determine whether they're trying to, move the right hand or not.
Okay.
Which is very useful in other cases. Let's go ahead and, so it's just a basic example, but this is just a notebook to introduce EEG for anyone who might not be familiar, but is interested in learning how to use this.
Sure.
And luckily, this is actually using an open source data set. So if you're interested, you could also just go to the MNE website, download their package, just doing a regular pip install MNE. And from there, they have a default sample data set that you can play with.
Okay, fantastic.
And then, of course, some other notebooks that just show how you can extract the data and form CSVs from them, for example.
Okay.
And then process them in different things to run things such as classification. This is a very rough one, though. This is very, very quickly put together. So it's not the best classification algorithm, but it is something.
And so with that classification algorithm, you're basically taking all of that EEG data, doing all of the cleanup analysis, removing the noise, all of those things, and then you're trying to classify whether it is...
Good question.
Okay.
So I'm using a different data set here in this notebook.
Okay.
So here I'm looking at another open source data set called OpenMIR, MIIR, for musical information retrieval.
Okay.
Which is a really cool data set where people have EEG.
Okay.
So they have their brain signals recorded as they're listening to different audio clips.
Okay.
So listening to familiar songs and maybe not so familiar songs. So things like Mary Had a Little Lamb, Take Me Out to the Ball Game, etc. But they're asked to listen to the music and just have their brain signals recorded while they're listening. Okay. And they're also asked to listen to the music and then kind of imagine what comes after. So they're given a set of beats that set the tempo. And so they're like, okay, I think this is going to be Chim Chim Tree. And then they have to imagine what that is. So there's a whole data set on, just their EEG with these different situations. Okay. And so what I'm doing for classification here is trying to understand, just from their EEG, can we tell what song they're listening to? Okay. And so this was, very quickly put together. It's not, I need to really revisit the model just to make it, actually work. So I need to do more pre-processing. But the basic premises of this is that you can use the data that you extracted from the first notebook or Epic extractor, pull it into this notebook, read the actual data. Let's see, it's just showing the shape of it, and then run whatever you want to try to classify the EEG. And so here I'm just using the raw EEG as the entire samples per second or per very small amount of time. Sure, yes. For about a few seconds. Okay. So there's just a lot of those. I have about 600, but that's still not a huge number in terms of big data. If you're working with a common image data set, for example, you have hundreds of thousands, lots of them. So this is small, so I just went with a basic, what do you go with, SVM, possibly multi-class SVM. I'm just showing how you can visualize things in here. But yeah, I don't have to go into the actual classification here, but the whole premise is that you can actually run it in here and you can use your package of choice. So for example, I'm just using a standard scikit-learn library I just imported.
Yeah.
So nothing proprietary by Microsoft or anything, it's all open source.
Yeah, that's fantastic. So you were able to build this model to classify, and then how, what does the accuracy look like? Were you able to tell what song they were listening to?
No, so unfortunately, this should work in theory once I do some more feature engineering.
Okay.
But unfortunately, since I was limited on time, I just threw the entire thing in there. I was like, okay, well, do your best.
Yeah.
But because this is more of a regular supervised learning approach and it's not something as complicated as convolutional neural networks,
Sure.
It doesn't have the chance to learn any select features and try to understand the data more. So unfortunately, this is at about chance level right now, so it's not that great. But
no, but it's a fantastic starting point for anybody that wants to dig in with this stuff.
So I want to definitely give this another day or two and actually just get something out that has a fun way of classifying EEG depending on what you might be listening to.
Okay, very cool. Yeah. What other applications of this, of applying AI for neuroscience do you see?
Yes, so this was just like a fun example just to show a starting point.
Okay.
But there are many, we can say clinical applications you can run as well, and definitely a lot of research applications.
Okay.
So for example, one thing that might be of interest is understanding things about epilepsy or any sort of like motor, things that inhibit just regular motor function throughout the day.
Sure.
So for example, if you have some form of epilepsy that's not really treatable by medication, then sometimes you go into the hospital and you get consultation, and they might suggest you get surgery done to find the location where the seizures might be happening.
Sure.
And then if it's a brain area that's okay to take out, then they'll go ahead and actually take a chunk of the brain out. So this is actually the patient population that we work with in the lab that I research in as a graduate student. We don't necessarily work with epilepsy but we do work with these patients.
Okay.
Because while they're there, they have a grid of electrodes directly implanted, so it's placed directly on the surface of their brain, rather than having like the swim cap on top of your head.
Sure.
So because of that, you have the electrical activity that is at a much finer spatial scale, and you can have a lot better signal-to-noise ratio, understand more about local activity, et cetera.
Sure.
So let's say, for example, that I were to use Azure Machine Learning Workbench or just some of the machine learning applications from Azure. Let's say that I have a lot of this electrocorticography or ECOG data, this brain data, from these subjects, and I want to understand when their seizures might be happening.
Okay.
So if I were to use something like this, I'd be able to import the data, hopefully time align it with some of the information from some of the clinical staff on when seizures might be happening, and then after the fact, create a model that uses the training data that knows when the seizures are happening, and then possibly gets information to predict when a seizure might be happening.
Oh, wow.
So this is something that is might be able to help, for example, the clinical staff. Yeah. Like giving them like a few second warning, like, hey, something might be happening, so be prepared. But if we extrapolate this to EEG, where it's non-invasive, of course the data is a bit different because it's non-invasive, so it's not as clear. But if we could create something like that, maybe there could be some home monitoring that if someone's interested, they could use their own commercial EEG, for example, and say, okay, well, I'm kind of new to this. I've only had epilepsy for however long, maybe it developed recently. And I'm interested in understanding what might trigger it or what might happen, when it might happen. And so if you had a home monitoring system, then maybe you could, download embed the model into your own local machine. Or if you use cloud services, maybe it's something that's running in the cloud. So you don't have to have a high-powered machine to run it, which is definitely, something you're interested in if you're, if you don't have like a huge, powerful machine. So
absolutely. And so this could be something where that model could be trained to learn and understand the signs of precursors to potentially epileptic attacks.
Definitely.
And then warn the patient or the person. Oh, that's fantastic.
And I feel like we'd probably, this is something that I hope we can do in the future. And not by hope, we can actually do this. It's just a matter of actually getting it done. And making sure we have all the right approval, making sure everything's correct.
FDA and all the things.
Yes, make sure it's correct. But if we can get information and train a model off of a lot of different subjects, and then have, let's say, just basic weights that might work for most people, And then you have a training period, or it learns to adapt to the
That
individual user.
individual, yes.
And then the performance gets better and better.
Sure.
So that's, kind of the great thing about AI and machine learning, is that it's really personalized.
Personalized,
Yes, there you go.
Patient.
Yes.
Fantastic. Well, wow, this is super cool, and I think probably one of the most bleeding edge applications that we've seen of this. So just fantastic stuff. And then, so are we going to post this and make it available for people to dig into?
So not yet, but we are planning on releasing something, which I can't go into detail now because we're still working on it.
Yep.
But we are planning on releasing something where everyone can get a chance to start to play with neuroscience data, contribute their own, and really hopefully just help boost the field and help get people who are interested but kind of scared by, the giant barrier that it is knowledge about neuroscience.
Yeah, absolutely.
At least get them involved and understand that, even with the very basic understanding of neuroscience, you can start to help uncover more information and help the field in general.
Fantastic. This is great. Thank you so much for pulling this together. And with that nice teaser, stay tuned, and soon we'll see more from Niall and from this great research. Until then, go to AI School and learn about machine learning and AI technologies, and happy coding.